So today I'm going to say a little bit about some of the work we've been doing in my lab over the past year or so. And I know this is the last talk, so feel free. I don't have to get through all the material. Feel free to interrupt me. If there are questions, happy to take them as I go along. So one of the questions that I've been very interested in for the last several years is how do we make real use of a lot of the exciting data that's being collected in what we call biobanks. So these are these data sets that are putting together genomic data with all kinds of other phenotypic and observable data. And how do we actually make these connections between genetics and genomics and health outcomes? Today, I won't say too much about genetics, but instead, I'd like to say a little bit about all the other exciting data that is being collected as part of these biobanks. So you not only have genetics and health outcomes, these biobanks are now beginning to collect other types of data. For example, imaging, molecular data like gene expression, or wearable data. So previously, if you were only trying to make connections between genetics and, say, disease status, you'd build models which are trying to say, okay, whether somebody's disease status is coded as a 0 or a 1, or whether it's a continuous measurement. How do we build models that link genetics to that particular outcome? Now, what becomes interesting when you have these other types of measurements is they are high dimensional and they have structure associated with them. So the challenge moves from just making links between genetics and phenotype to actually deriving phenotypes themselves. So how do we take an image and derive or extract relevant features from an image? So phenotyping becomes an important first thing that you would want to do when you have these types of data modalities. So the problem that we are facing is we have data of different kinds, and we'd like to transform it into a representation that we can easily work with. So typically what this means is this would be some vector space that we would map this data into. So whether it is text, image, audio, time series, could also be structured data. It could be a table. We'd want to find a function that maps all of this data into some vector-spaced representation. And typically, we call these functions encoders. And this problem of mapping data into a vector-valued representation, that's typically what is the purview of representation learning. So now the question is, what do we want with this representation? What are the goals of trying to learn a representation like this? So one goal is we don't really care about this representation as such. We think of this as an intermediate, and we want to use this representation for some downstream application. So we want to use this maybe for some predictive task. So that is one possible goal where we want to learn representations that are predictive. So this is one approach to representation learning. But there's another goal, which is we don't have a very specific downstream prediction task in mind. We want to learn representations that are broadly useful across many possible downstream tasks. So in this case, our goal is to learn what we call a meaningful representation. So we want to learn a representation that is capturing the underlying semantics, the underlying meaning of these data. So for example, if you were dealing with natural language or text, so you might want to learn these representations, which might be hard to see here. So these are what are called word embeddings. And these word embeddings learn representations which group together semantically similar words. So for example, in this figure here, all the names corresponding to countries map onto a closed set of coordinates in this space. Their capitals map to another closed set of coordinates. And there are vector operations that map country names to capital names. And what is remarkable about this is the model during training has no idea of these semantics. So these semantics emerge post-training these models. So in this context, there isn't a downstream task. So we'd like to learn these representations that are meaningful. And the challenge is, because there is no downstream task, this has to be done in an unsupervised manner. So how do you go about achieving this? So we will essentially convert this unsupervised learning problem into a problem which we can solve and that's supervised learning. So although our goal is unsupervised representation learning, we're going to solve this by the use of supervision. And to do this, we'll have to create these supervised learning problems. So in the context of text, for example, we will create a problem which says, let's try to learn a representation which is going to allow us to predict words surrounding a focal word that we might be interested in. And these go by different names. They're sometimes called pretext tasks. And the hope is by picking an appropriate self-supervised representation learning paradigm, you might actually be able to learn meaningful representations. So at the end of the day, self-supervised representation learning is coupling some type of encoder with some type of this pretext task. And by mixing and matching these, you get different possible paradigms for self-supervised representation learning. So let me just tell you about one possible choice of, say, an encoder that you might use. And this is something that has been extremely popular. I'm sure you've heard of it in many different contexts, but just so that we're all on the same page. So if you're dealing with language or text, one property that you want this encoder to be able to have is a particular word in the text should be able to pick up its relationship with all the other words in this sentence. So you want this context to actually filter into any such word. In this example, you want it to be able to refer to the fact that it refers to the animal in the sentence. So this is something that the model needs to be able to learn in an unsupervised way. So a challenge with building these models is oftentimes context is stronger from things that are close by than things that are further away. So we want architectures, models that allow us to pay attention to things that are even further away from the word that you're trying to predict. So one such architecture which has been very successful in doing this is a transformer. So the transformer is basically this map which allows you to learn these attentions in a data-driven way. And these encoders stack together many of these attention blocks. So as you move further and further up these attention blocks, you pay attention to different parts of this sentence while trying to make your prediction. So this architecture, it had its origins in language, but it can also be applied in other contexts for other types of data. So this has also been applied to image data. So image doesn't have a natural sequence like in a sentence. So when you're trying to adapt these types of architectures into an image, you have to create a sequence. So in this vision transformer architecture, the original image is broken up into smaller sub-images. We call them patches. And then you feed them as before into this encoder. And by, again, composing many of these layers, you build the ability to pay attention to different parts of the image. The first vision transformer paper introduced this in the context of a supervised learning task. And then there were subsequent works that introduced vision transformers in the context of self-supervised learnings or an unsupervised setting. So what they did was essentially they looked at different views of the image, say a rotation or some kind of cropping, and they would feed it into two different neural networks and see whether the representations learned are aligned with each other. And so this transformer would actually learn attentions which were quite semantically meaningful. So if you were to look at this figure and you were to look at what are the parts of the image that this model is attending to, it looks like it is picking up semantically meaningful parts of this image. So this is how semantic information is emerging from these types of architectures. So this is just a bit of a primer on what is going to be the basis for the rest of my talk. So I'll talk today about using these types of ideas in the context of two different modalities. The first one is 3D medical imaging data, and the second one is going to be tabular phenotype data. So as I mentioned at the beginning, biobanks, they collect a variety of different modalities. Many of them are images. Many of these are 3D images. So you have things like MRI, CT scans, OCTs, and so on. And extracting images from these modalities is quite challenging. Even from a single image, it's quite challenging. 3D images is even harder. And so the question is, how do you actually build these types of representations for 3D images? And as I mentioned, the paradigm for 2D images is you have a massive data set of 2D images from the internet. And now you train one of these models, say a transformer architecture, in some type of pretext task. So that's the pre-training. And then you have some downstream application, so you apply to this task, either with no fine-tuning or with some small amount of fine-tuning for that task. And this basic paradigm has led to many different 2D image foundation models over the past few years. However, when you talk about 3D images, there hasn't been the same kind of success or the same kind of development, and there are a few reasons why that hasn't happened. The first is just storing and computing on these 3D medical images has a high cost associated with it. For those of you who work with these data sets, you're probably aware that most of these data sets are now actually on different cloud computing platforms, and actually performing many of the operations, many of the learning steps you need for learning these models is actually extremely expensive. The other thing, of course, is medical volumes are fairly uncommon. So if you look at the sizes of the largest training data sets for medical volumes compared to 2D images, there is about 2 to 3 orders of magnitude difference in these sizes. So what that means is you really can't have these highly parameterized, say, million, billion parameter models trained on these types of data sets. And of course, the other challenge here is if you were to take a deep model that has been designed for 2D and directly generalize it to 3D, they typically do not scale well for volume. So if you just take a CNN, a ResNet, and convert it into its 3D equivalent, just training those is going to be extremely challenging. So this is a paper from 2024. It's one of the state-of-the-art for medical volumes. And essentially, they had to spend close to hundreds of thousands of dollars to be able to train their 3D medical image model. So these are some of the challenges that led us to ask whether there is a way for us to leverage the advances that we have in 2D foundation models to learn 3D representations. And can we do this without having to go through this very costly training process? And of course, do we end up learning a representation that is both compact and useful? So let's see how we might try to do this. So let's give a thought experiment. So we have a 3D volume. And one of the ways you can think of this is you can think of it as a sequence of 2D images. And we can apply a 2D foundation model to each of those sequence of images. And now you concatenate all of that, and that is the representation that we might want to deal with. Turns out that's not a great idea, because if you start with a volume, and so a typical volume might have a size like this, and you were to use this approach where you go slice by slice, apply your 2D foundation model and concatenate all of it together, you end up with a resulting representation that is substantially larger. So this is not something that works well, especially at scale. So now the question is, are there ways of compressing some of this information while still retaining the key signal here? So this led us to the idea in a method which we call Raptor. So what Raptor does is it goes slice by slice, as we said previously. And instead of just taking each of the outputs of these 2D foundation models per slice, we do two things. The first thing is we actually do what is called a planar reduction. So we are going to actually sum up all of these foundation model outputs across the slices. And before we do this, we will also apply a random projection to each of those slices to reduce the dimensionality. And so this is going to give us a tunable parameter. So the random projection essentially takes the output of the 2D foundation model. You multiply it with a random vector. So typically, random Gaussian is what we use. And there's a question of how many such random vectors we should be using, how much retains signal, how much do we need for compactness. So what are the benefits of this approach? So firstly, there is no training involved, so it is extremely fast. So we're taking existing pre-trained 2D foundation models, and we're applying it to the 3D image data set. There is this aspect of this tuning parameter, which is this compression ratio, which is determined by how many random projections we use. So that is going to be a trade-off between signal quality and compression. And another benefit is, as you have your favorite 2D foundation model, which grows in terms of its parameter count and its expressiveness, you could reapply those to improve performance on 3D data. So this is the basic idea, and now the question is, how does this approach work? And I guess the tradition in CGSI is we don't spend too much time on results, so I'll go quickly over this. Feel free to ask questions if you have specific things you'd like to chat more about. So this is an experiment where we were looking at several different data sets, 3D medical image data sets. So one set comes from something called the 3D medical MNIST. So this looks at a variety of different modalities for different conditions in different tissue types or body parts. We have some chest X-ray data sets, and then we have a brain MRI data set. And what we did in the paper, we don't have it here, is we've compared it to training and testing 3D models from scratch. And then you have these other approaches, which are pre-trained models of different kinds. They vary in terms of which data set, architecture, and how they do their fine-tuning. So generally, what we find is Raptor is quite competitive. It actually does very well in terms of its accuracies. There are some data sets where it does not so well, and there are reasons I can discuss offline for why. The other interesting aspect is the embeddings that we get from Raptor are compact. So here, what I'm showing is the accuracy on these different tasks, the average accuracy, as a function of the memory footprint. So the memory footprint is determined by this random projections parameter. And you can see that with a relatively low memory footprint, Raptor has quite accurate predictions in these downstream tasks. So then we decided to ask, what can we say about the quality of Raptor embeddings for very specific downstream tasks? And for this, we looked at the brain MRI data from the UK Biobank. So this is data where you have, for every such MRI volume, there are expert-defined features. So these are features like the volume of white matter or whether there is differences in the surface area. And so these are things that are obtained by very specific kind of image processing methods. And so we asked the question, if we were to take the predictions from the embeddings from Raptor, and we looked at another model which is trained on scratch from this. So this is a 3D ResNet. And we were to try to predict these IDPs. What do we see in terms of prediction accuracy? And what we see here is, so here we are looking at Raptor for different values of this compression parameter. So there is no compression here on the left. And then we have increasing compression as you lower the dimensionality of the random projections. And so actually, the arrow is pointed in the opposite direction here. And what we see is, in general, the accuracy of predicting these IDPs is higher. And it's higher, of course, when the compression is lower, which is as expected. But even with substantial compression, it gets accuracy that's comparable to using or training a 3D ResNet. Of course, the nice thing about this is you don't need to do any training on these data sets. We can ask other questions about the types of biological signals that are present in these embeddings. And to do this, we ran, in this particular UK Biobank data set, an association study, a genome-wide association study, on the IDPs. So these are the expert-defined features, and compared it to the association study results if we were to run an association analysis on the embeddings. So here we have the embeddings from Raptor, and we are comparing how many association hits we get when we compare it to the IDPs. So typically, the IDPs have about 100 such hits that we find, and Raptor has roughly twice as many. How many we get depends on this, again, compression factor. So as the compression factor is lower, there are more hits, which is, again, expected. So this is not a completely fair comparison, because it may be the case that this increased number of hits is simply because of differences in dimensionalities across the IDPs versus Raptor. So the Raptor embedding, depending on what value of k you have, might have different dimensionality, and that is quite different from the number of IDPs that we're dealing with. So to make it a more fair comparison, we did the following. So we took the embeddings from Raptor, we ran it through PCA, so to decorrelate the embeddings, and then we ran GWAS on each of the principal components. And what we're seeing here is, as a function of the number of principal components, how many hits that we find or how many loci we find. And we did the same for the IDPs. And what you can see is for a given number of principal components, the Raptor embeddings lead to more genetic loci being discovered compared to the IDPs. So this suggests, this is very much ongoing work, that these embeddings that are being learned tend to be more heritable, tend to have more genetic signal associated with them. Okay, so that was about 3D imaging. Yeah?
So all your slices are parallel to each other,
right?
You think about doing random projections also for the slices to get different angles before you do the...
Yeah, that's an interesting question. So the question is, can you do it at different angles and see whether that gives you certain features that might be missed that are only present at a particular angle? Yeah, the challenge there is, yeah, there is a design decision to make as to what angles to choose. Right now, we do it for X, Y, and Z. It could be random as well. And yeah, that's an interesting question. So right now, we don't do it. We just do X, Y, and Z. But yes, looking at random angles might also work. And this goes back to the question of when this approach may not work. And the settings where it doesn't work, we think, are where there is non-smooth variation across the slices. And so, yeah, these random angles or random directions might be able to get at that better. So it's a design decision. Yeah, we haven't explored that. Other questions before I move on to the next section? Okay. So now I'll switch over to the other data modality, which we have a lot of in these biobanks, and that's tabular data. And the particular representation learning question that we care about arises due to the fact that we have tabular data, but a lot of it is missing. So you're trying to do imputation. So imputation is going to be the task that we would like to solve while we're learning our representations. And the reason for this is missing data in biobanks is pervasive. Despite all of the scale that we talk about, a lot of the phenotypes that are relevant, that are things that people actually care about, are measured only on a small number of individuals. And this has many reasons: logistics, cost. Oftentimes, there is trade-off between measuring phenotypes very accurately on a small number of individuals versus measuring it approximately on a large number of individuals. So here's an example from the UK Biobank, which is looking at missingness percentage. And you'll see that most of the phenotypes here have very high percentage of missing data. So missing data is a big problem. But there's additional issues with the missingness in these biobanks. And this has to do with the fact that the missingness is not completely at random. So there is structure to the missingness. So to illustrate this point, here is an example. You probably cannot read this. But in this particular example that I have here, there are questions that are being asked, and individuals are answering questions. And depending on an answer to question 1, an individual is administered question 2. So if an individual answers no to a particular question, they would be missing for the following question. Or if they are missing for the first question, they might still be missing for following questions. So what that means is if you were to look at a data set like this, so if you look at individuals by features and ask who's missing and who's observed, you will see that there are these very distinct patterns of missingness that are seen here. So this is what we mean by the fact that missingness is structured, where there is information in the patterns of missingness over and above the values that are observed. So how do you solve this problem? So as you're aware, there are techniques for filling in missing data, imputation. And so the idea would be, you're not just measuring one particular phenotype, you are measuring a whole host of phenotypes, and there are correlations amongst them that can be leveraged for imputation. So in this example, the second phenotype is missing. So hopefully, we might be able to predict the second phenotype from all of the other phenotypes that are collected. So posed this way, this is just a simple prediction problem. What makes it an imputation problem is these other phenotypes themselves are missing. And so we have to solve a collection of supervised learning problems here. So that leads to the problem of imputation that we are dealing with. So this is, again, very well studied. And there have been many methods that have been developed for phenotype imputation over the years. But as we got into this problem, we found that there were still missing characteristics that we need from a phenotype imputation method. So the first thing is we want this method to be scalable to the kinds of data sets that we care about. We want them to be expressive, so not just linear models, but potentially nonlinear models. And finally, we want these models to be effective with the structured missingness that we talked about. So going beyond simple missingness completely at random. So the third one is actually the most challenging one, and I'll tell you a little bit about why it matters. So here's an example of a data set that we might be dealing with. And what you see here is in this data set, so phenotype 2 and 4 are missing together. So what we would want our model is to be able to learn the fact that phenotype 2 and 4 are missing together and be able to predict these two values together from all the observed phenotypes. So that's what we want in terms of being able to handle structured missingness. So how do these imputation algorithms work? So typically, we cannot evaluate their performance on truly missing data because we don't know what the underlying values are. So we're going to introduce additional artificial missingness. We often term these masks. So we introduce artificial missingness on actually observed values. We get the model to predict those masked values. And by comparing the prediction to the truth, we can learn the model. So the question is, how do we introduce this mask or artificial missingness? And one approach would be to randomly pick these entries and mask them. And as I said before, this is not a good idea, or we don't think it's a good idea, because the model is not going to be paying attention to the structured missingness patterns in the data. So we'd like the model to be able to pay attention to something like this. So one approach is, let's try to learn a model for structured missingness. So just like you have a model for the observed data, let's try to learn a model for missingness. So you might have a parameterized model to be able to do this. So that's an interesting idea. We did something a lot simpler, which is we said, let's simply sample from the empirical patterns that we observe in the data, the empirical mask patterns, and use that to mask our data. So in other words, we will sample from a mask pattern that looks like this and apply it to one of the rows of this matrix. So having done this, now the model is required to reconstruct entries 2 and 4 in this first individual, and you would then compare it to the original entries. So this technique, we call it copy masking. And so this is a way of introducing masked elements. And now you combine it with an underlying model for imputation. So in our case, we used an autoencoder. So we have an autoencoder coupled with this copy masking, and then you have a loss function that you optimize for this procedure. So this method, we call it autocomplete. And just to show you the value of this approach, so here is an example. This is a data set from the UK Biobank. It's a data set of psychiatric disorders. And what you're seeing is accuracy measured on the y-axis compared to how much missingness we are simulating. And we have this model that is being trained with uniform masking compared with the model with copy masking. And we see that no matter what levels of uniform masking we apply, copy masking always tends to do better. So this is telling us that there is value to actually modeling this structured missingness through copy masking. So then we applied this to a few different data sets, all from the UK Biobank. One is a data set of cardiometabolic, another is psychiatric disorders, and we compared it to other imputation approaches. So as a linear model, we compared it to soft impute. We also compare it to a classical nearest neighbors, as well as a couple of deep learning approaches. So the first thing to note here is the linear model actually does quite well. It's a very strong baseline. However, autocomplete, because of this combination of nonlinear functions and copy masking, tends to do better. So one of the nice things about these biobanks is, in addition to the phenotypes, we have the genetics. I said that's not the real focus of this talk. However, we can ask, once you have a better imputation of the phenotype, does it actually lead to downstream analyses? For example, does it lead to new kind of GWAS loci that are discovered from imputation? So this is an example of one particular phenotype. This is lifetime major depressive disorder, MDD. And what you see here is running a GWAS on observed lifetime MDD. So this is present only on about 20% of the sample, and then applying it to the imputed lifetime MDD. And not surprisingly, as you have more individuals with this imputed phenotype, that should lead to more power, and that is seen in this figure. So there are additional loci that are discovered that are associated with this phenotype. Of course, a concern in all of this is the imputation might have introduced biases that have nothing to do with the original phenotype. So are these discoveries truly MDD loci? And there are a few different analyses we did for this. The first one is replication in other data sets. So if you were to take what we discover in UK Biobank and see whether these discoveries replicate in other data sets, what do we find? We looked at both a data set within the UK Biobank as well as external data sets. And generally, there is pretty high replication of the discoveries. We can also look at polygenic architecture, like genetic correlation, and see whether the genetic correlation between the original phenotype and the imputed, or the imputed and the external, they are all consistent. So that's telling us that the genetic architecture hasn't changed too much. And again, the genetic correlation appears to be quite consistent across imputation and both observed and external data sets. Yeah?
Quick question. How can the genetic correlation could be over 1?
The
RG is on the y-axis?
Yeah, so these are estimates, right? So we don't constrain the estimator to be between 0 and 1. So the estimator can actually vary. It could also, yeah, so there is no constraint on the estimator. Okay, so that was like a first attempt at imputation. And of course, the question is, are there ways of improving our imputation? For example, so this is a general kind of framework. There is the model, which is basically an autoencoder model. And then there is the simulation of the masking strategy. And can we improve either of these axes to lead to better imputation? So the first thought is maybe we can move from the autoencoder to a transformer architecture. So that seems like a natural thing because transformers tend to be more expressive, so potentially that can lead to a gated accuracy. And turns out there are some complications in doing this. If we were to naively apply a transformer architecture using the same kind of copy masking strategy, the transformer actually doesn't learn very well. And the reason for this is when you have a lot of these masked tokens, so they are basically null tokens. So at a certain point, you have too many of these null tokens, and as a result, these transformers, they learn very slowly in the presence of these null tokens. So there is this kind of neat trick that Adi, the student who was working on this, found, which is called median truncation, where the idea is essentially you permute the features and you only look at the first 50% of the observed, and that leads to much more efficient learning. I can give you more details of why that works. Another interesting idea is there additional information to be gained from prior knowledge about these features? For example, many of these features have text associated with them, or you even have the names of these features. And can we use this information to figure out which features might be informative for which other features? And so to do this, we actually use what we call context. So we have a model which takes all of the text information, so feature descriptions, feature names, puts it into a language model. And this goes as an additional kind of entry into the vectors that we learn associated with each feature. So we have this new method, which is now combining both context in the form of these text embeddings, as well as the regular transformer. And then this is all learned through copy masking with these additional tricks that we mentioned. So we applied this to a bunch of machine learning data sets. So these are not biomedical data. So these are data sets that have been typically used in a lot of the ML imputation literature. And we find that this approach, which we call cacti, improves imputation accuracy over other approaches under different missingness settings. We also show that this median truncation copy masking improves over what we call naive copy masking. So when you have naive copy masking, because of the fact that as you introduce more and more of these null tokens, the transformer is unable to learn effectively, we find that the accuracies are never quite high. Whereas when you have median truncation, as you increase more of these null tokens, the model is still able to respond and increases its resulting accuracy. We also find that context helps. So we have this language embedding, which tells you what might be the features that are correlated with each other. And across these different settings, we find that context can provide statistically significant improvements. So that was all on ML benchmark datasets. Then we applied it to the UK Biobank datasets that were previously described. So this is the psychiatric disorders and the cardiometabolic dataset. And we find, again, this new approach, cacti, improves over prior approaches. And there is an interesting experiment observation here. So what we find is when we look at the ML benchmarking datasets, when we look at the other approaches, the rankings of these approaches is quite different compared to the ranking on these biobank datasets. And we think that that is reflective of the fact that these datasets are having very different properties in terms of missingness. For example, in the ML datasets, the original datasets are completely observed, and then there is additional missingness that is added onto them. Whereas in these biobank datasets, there is already substantial missingness, a lot of structured missingness, and over and above that, we are adding missingness for these assessments. So it's actually quite interesting that there is this gap between performances that we observe on the ML versus these biobank scale datasets. Of course, we also have the genetic information, and this is all very preliminary. So if you have better imputation, in principle, that should lead to more genetic discoveries. And that is also something we observe for the traits that we previously looked at. So even compared to autocomplete, cacti has additional genetic loci that are being discovered. OK, so just to quickly conclude, hopefully I've given you some ideas of both the challenges, but also some of the cool questions that you can begin to think about with these multimodal data sets. And some of the key findings for us is that the 3D medical images are compressible, and these compressive representations can have a lot of semantic information. The effectiveness of random projections is always a surprise, and when it works, it is quite interesting to try to understand when it works and why it works. So as I mentioned, it does rest on some assumptions about how the features in these data sets, how smoothly they vary across the images. Coming to the missing data imputation part of the talk, I think this idea of structure to the missingness is really important, but underappreciated. It's something that we and others are now beginning to look more closely into. And how do we actually include the structure in different ways into the learning algorithm can potentially lead to quite a bit of improvement. And with this, I'll thank all the collaborators, the students who led the work. So the work on cacti, so this was led by Adi, and the work on Raptor, so that was led by Ulzi and Bronson. Yeah, and happy to take any questions.